So the previous class, we, basically ended with a challenge, right? So trying to show that when you leave the world of just utility maximization, you also lose the properties that we just proved are equivalent to utility maximization in finite choices, which are completeness and transitivity, right? So I described a new model of behavior that instead of having just one utility, it has a collection of utilities. And then my preferences are defined such that A is preferred to B whenever all utilities in a unanimous way agree to rank A above B, which is mathematically equivalent, right, to taking the minimum over all the possible utilities, and then only ranking A better than B whenever, according to the minimum, right, of this difference of utilities, the difference is still weakly positive, right? Now, okay, so my claim was that when you do this, you end up with a possibly violation of incompleteness. So I created the simplest example possible. So X, an abstract set with three items, A, B, and C. And then I declare, these three utilities. Utility 1 that ranks first A, then B with number 2, right? And then C with 1. So this is a utility such that the ranking induced by it will be A, B, C, strictly. Utility 2 does the opposite. So takes A and assigns a value to 1, B equal to 2, and C equal to 3. And then utility 3 does 2, 1, 3. So the most ranked one is C, and then you have the middle one, right? Now, since you know from observing this that the difference from A and C from utility 2 is -2, right? And the difference between C and A in utility 1 is -2 as well. So if I take the minimum, right, of this difference of utilities across all utilities 1, 2, and 3, my value is going to be strictly less than 0, right? In fact, it's going to be less than or equal to -2, which means that neither A is better than C, nor C is better than A. Do you understand? So basically, I just have to find one utility such that A and C will be less than 0, strictly, and another utility, right, such that C and A, the difference will be strictly negative. So that is a guarantee that when taking the minimum, I will have always a negative value, and hence I will never be able to rank A and B. So this particular decision maker doesn't know how to rank A and C. Okay, so what is intuition? I mean, this person is endowed with three criterions, right? Each of them is ranking very differently alternatives, right? So when you're trying to aggregate, this person is cautious in a sense. So it's taking the worst case, right? So the minimum over all criterions. And then, given this cautious behavior, then this person is going to not be able to conclude whether A is better than C, right? So it's inconclusive. So I don't know how to round them. Okay, so of course, what is the issue here? This is not utility maximization, right? So it's in fact a multi-utility representation. So this model is important because of two reasons. First of all, as you can see, if you have this ranking, right, as I define it here, and you observe A is preferred to B, then you can find a utility that ranks A better than B, right? So this is the part of the proof we studied yesterday, right? The second thing we observe is because you don't have a unique utility, right? A unique ranking, right? Then basically you end up losing completeness, right? So completeness essentially and transitivity, they amount to having a unique criterion, as we remember in the representation theorem. So if you have a mapping U that is such that U of A greater than or equal than U of B, even only if A is preferred to B, right? Then it has to be that this preference relation is complete and transitive, okay? So when removing the uniqueness of the utility in the sense that there is a unique ranking, right? You can have different cardinal representations, right? So for instance, the numbers can change, but the thing that must remain the same, right, is the ordinal representation. So as long as you have a unique up to monotone transformations, right? So unique ranking in the utility, you're gonna have completeness and transitivity, right? So any departure from this model is gonna break possibly either completeness or transitivity because the link is tight, is if and only if, right? So moving away from utility maximization means moving away from transitivity and from completeness, or from completeness. Okay, so I mean, some of you send me the solutions by direct message. Great, that's what you should be doing. I hope also you try at home the solution. I provided mine so you can compare. And this, is a kind of a example of.
Sorry, I have a question.
Yep.
In example 12, is the element B redundant?
Is redundant. So
the element B.
Yeah, so you're trying to call it redundant. What is your reasoning?
Because in this example, only the element A and C is incomplete. So the element B is not important in this example.
Yeah, so, that's a good observation. In particular, right, this model may, is doing more things than just failing completeness, for sure. Now, one thing that has to happen in this model is that the model has to be transitive. Besides that, there is no really general pattern. So that may be a particular, feature, and this interpretation, might be well brought, upon us, but basically it's not a general property of these models, right? It's just an artifact of my particular example, right? So whatever additional pattern you see, the only pattern that is always general in this model of multiple utilities with unanimity is the transitivity property, right? So these models are going to be transitive, right? They fail completeness and they may fail other stuff. So any additional pattern is also kind of spurious in the sense that it's going to just arise given the particular choice of the example, right? So particular ranking I provide. But a general multiple utility representation with a unanimity is going to just be transitive, okay?
Okay, thank you.
Okay. So again, one thing that I want you to realize. So this example basically allows me to clarify that there are other models besides utility maximization, right? First thing. Second thing, right? Utility maximization, even if powerful and being, the cornerstone upon which econ has been built, right? Is not really, a very flexible model, right? It might seem so, right? It might seem that, being utility, fully non-parametric utility is a very general model. It's not, right? And it is, in particular, it gets more stringent when the decision at place is more complex, right? And, in this example with 3 alternatives, it's not necessarily complexity of the choices, like you have too many alternatives, but it's complexity of how I'm able to rank them. Now that we live in a complex world, like, for instance, again, talking about the decision to lock down, should we open primary schools in Ontario or not, right? So, fully open, mix, always Zoom, right? 3 alternatives. So what is the best way to rank them? Unclear. You may have multiple criterions, right? Some committee should decide that the only way you take decisions is by unanimity, right? Only if everyone agrees, we should rank this better than this, right? So, some alternatives may be clearly ranked, others may not, right? So for instance, is A better than C? Is truly, fully opening better than Zoom? I don't know, right? Many things going on, different criterions, okay? So my point is that, utility maximization, despite the fact that, has been traditionally the main element in the toolbox of economists, is very restrictive. So I want you to understand that, but, this is kind of a claim right now on the intuition level, right? So I just trying to convince you informally that this is true. In the end, we're trying to do science, so you should start thinking, whether the empirical implications of utility maximization, right? So start thinking that, this is a model, right? A model of behavior. Hence, you should start asking, okay, but what are the observable implications of such a model of behavior, right? What kind of data do I need to test this model? And how should the choice data look, if it were generated by utility maximization, right? So start thinking about that. We're going to get eventually to that in this class. But, right now, all of this is a model, right, that I claim is a good description of behavior, okay? And, economists have been able to do a lot of discussion and philosophizing, and sometimes even, quantitative models using that model. Have we really tested this model? Do we have clear evidence that it works or not? That's a little bit something that is in discussion. We're not physics, right? So it's not that this is the general relativity, right? The current accepted paradigm is only accepted because of tradition, right? Because Mascolel at Harvard told us to do it, right? Not only him, other smart mathematicians, but there is no really proof, right? So, okay. So I want you to start thinking about the empirical implications of the model, okay? But also realize that this is just a model, right? It's one particular way we try to describe choices, and it's not a particular flexible one. So there must be some restrictions, right? So not every possible behavior can be mapped to utility maximization. That's my main point, right? So it's not an empty model, okay? Okay, so now...
Could I ask you something about the proof?
Yes.
A very short question. So you proved that in the case that the second hand of the tautology does not hold, then the preferences are not complete. But in terms of the proof, is it necessary to prove the other way around? That is, if preferences are not complete, then the second part of the second hand of the tautology does not hold, or isn't necessary?
You mean here in this proof?
No, in the proof of the example we just saw. We saw the example is that show that the following preferences are not complete, are weakly preferred to be if and only if the utility of A is greater than B. So you...
Okay, you're asking about the question and if we did it completely, right? So it's about the structure of the question.
Yes, so what I see is that here you prove that when you give an example that the second hand of the tautology doesn't hold, then the preferences are not complete. Do we have to do the other way around as well in order for the proof to be complete or not? So for example, starting from the left hand saying that I give an example of some preferences that are not complete, then the second hand of the tautology doesn't hold.
No, so this is a type of question that is, is a format, right? So it's show that something doesn't hold. So you just go to the definition, right? So completeness, as I told you in the previous class, is defined through a universal statement, right? So for every alternative in a choice set, right, it has to be that I'm able to rank A above B or B above A, right? That's a universal statement, a universal quantifier. So in order to establish that something is not a property with universal quantifier, a sufficient proof is to provide a counterexample. So a particular instance of two alternatives in a particular choice set such that completeness fails, right? So I cannot rank A over B, A over C, and C over A. That's a sufficient counterexample. This constitutes a proof because the completeness is defined through a universal quantifier, right? So any statement that is for all, right, can be disproved by a particular construction, right? So that's basically like the example of, all swams are white, right? So if you find, you just need a black swam, and then you disprove the statement, right? So that's the kind of thing. So universal quantifier, all swams are property, right? I just find one that doesn't have the property, and that is a swam, right? And I'm done. So this is the same. right? I just found your black swan, and is this proof? Okay.
Okay, so once you prove this, you don't need to prove that starting by incomplete preferences, the second hand of the tautology doesn't hold. Okay.
Yep.
Great.
Yeah.
Okay.
Yeah. So the first part is the same, right? So show these things are not property, right? So given that the property is universal quantifier, I just need a counterexample. Okay. Now
Great.
it's tricky, right? Imagine I will have told you. So imagine show that the following preferences are not something that is existential, right? So there exists something, right? ... Then you have to show that for all cases, there is no such a thing, right? So then you have to do a for all proof, right? So it's always the negation. So negation of existential is universal. Negation of universal is existential. So when you are negating, as in this case, a universal statement, right? Then it's very easy because you just have to find one example. Well, it's not easy. Finding a counterexample is tricky, right? But that's the technique of the proof. You have to find the black swan, right? When instead you want to negate something that is existential, you have to prove for all instances, okay? That such thing doesn't exist, okay? So this is it's basically a proof technique. So kind of a rule of thumb is focus on the property, identify the quantifier. Completeness is universal, right? And then, basically, if it's universal, you just need a counterexample to disprove it, okay?
Okay, last question. It will be okay to, instead of giving a counterexample of the second hand of the tautology, give a counterexample of the first hand of the tautology. That is, I provide an example with two consumption bundles such that there are no complete preferences, then the second hand of the tautology does not hold.
Yeah, so tautology, I don't think is well used, right? So tautology is just a construction, right? Where it's a special construction where basically true implies true, right? So that's something, that's not what is this, right? This is just a logical proposition, right? So you just want to show something has there are preferences, right? That are not complete, right? That's the only thing I'm asking, right? And a complete proof is basically a counterexample, right? That's it. Now, I don't think in this case there is other way to prove it. Yeah, there are no other. Yeah, I don't see any other way to prove it. So basically, the only way to do it, I think, the reasonable way would be to do a counterexample. Okay. Yeah, the thing you were suggesting. So you're trying to do some sort of.
So I am suggesting starting by proposing A and B such that the preference relation is not complete. Then I prove that the second part of the proposition does not hold. That is, the utility of A is not greater than or equal than the utility of B for all the I's.
Yeah, but I mean that's a well-formed logical statement, but you are asking other thing, right? So you're asking basically, so if I have some preferences that are not complete, right? Show that there is no utility function, right? That's a different thing.
Okay, yeah, that was my question. Okay.
Yeah, but that's more related to the previous thing. So I didn't ask that, right? But you can also show that. So for instance, you can show that, and that is true, in fact. Why is true? Because if you go to the previous theorem, it tells you that the connection between completeness and transitivity is even only with the utility, right? So it's two ways, right? So it must be that, for instance, if completeness fails in the preference side, there is no utility, right? Okay.
Yeah.
Yeah. So now you have to be careful, right? It's all about quantifiers. For instance, one thing that happens also in the previous theorem is that imagine you just have transitivity. You can show that there is one utility that basically is such that if A is preferred to B, utility of A is greater than or equal to utility of B. So in fact, this is an instance, right? So you just have many utilities instead of having one in terms of ranking. When I say there is one utility, it's about just up to monotone transformations, right? So the ones that preserve the ranking, okay? Yeah, so the main thing that you have to remember is that there are some issues when you move to choices that are not finite. And in fact, these equivalence breaks in cases such as the lexicographic preferences, right? If you have the plane as a choice set, R2, lexicographic preferences do not have a utility representation. So what is missing? So what is missing is a technicality. The technicality that is missing for infinite choice sets is continuity. So basically what I need is that you need to basically take this additional property that is not really behavioral. It's basically a property that is technical. And it's telling you that if you have a sequence, you know, in a space that has a topology, right, and you can take sequences. So imagine the reals for now and for this class. And you take xn and prefer to yn for all n. And then, you know, if xn is convergent to x and yn is convergent to this, let me close it. I think I closed everything. But something is sounding here. Okay. Yeah. So basically you do xn to x and yn to y, then it has to be that in the limit also x is preferred to y. So the classical counterexample is going to be done in the world of lexicographic preferences. So when we study this more formally in a bit, I'm going to provide example with the lexicographic preferences, but bear in mind that continuity of preferences is not really a behavioral property, it's a technical property. Why is not behavioral? Because it's not testable, right? So you can never test this in any experiment, even if you have infinite time and only if you have infinite time, right? So you basically have to check, you know, infinite numbers and then basically test this in the very limit. So this is not testable. But, you know, in terms of math, you need to add it in order to be able to provide this theorem that now is stated without proof, but we will prove it in a bit. So not today, but in some classes. So if preferences are complete, transitive, and continuous, so I added continuity, then there exists a continuous mapping, U, going from X to R, such that U of X, the utility of X is greater than or equal to utility of Y, if and only if X is preferred to Y, for all X and Y. So, and also, this is important, if preferences are represented by a utility, then there exists a monotone mapping F. So a monotone mapping is any mapping, any function that is a monotone function. So in particular, take the utility function and elevate it to the power 2, right? Power of 2. That's a monotone transformation, right? At a positive constant, that's a monotone transformation. What is not a monotone transformation, right, is something that is, for instance, wavy. So imagine you take, and it has to be also strictly increasing, right? So you don't alter the ranking. So what we mean by monotone basically is something that preserves the ranking, right? So in other words, such that the F union in composition U also represents the preferences. So if you take, for instance, something like the cosine function, right, that's going to break the relation. So that's non-monotone. When I say unique utility function, is always up to a monotone transformation, right? So there is no cardinal meaning at this stage. There is only ordinal meaning, okay? And so with that in hand, I think this is basically the main part that I want you to cover from this thing. So if, depending on your background, so you may find it useful to go over the rest of the chapter, but we're going to cover it anyway, all the topics here in more depth in chapter 5. But this is kind of a reminder or refresher of a lot of topics of masters, right? Kind of, it's very master's level, a little bit honors if you want. And similar chapter 2. Chapter 2, you know, is a little bit of an awkward chapter because it introduces some notions of Slotski matrices and other stuff that we're going to see anyway, but it doesn't have much really punchline. So I decided basically to read it, to leave it as a reading assignment if you want to, right? So
Professor,
yeah.
Sorry. So your notes are based on the book, correct? The
So
microeconomic theory.
partially. Again, now
Partially.
the main source of the class, as I mentioned, right, is the notes, right? The main resource. Some of them, when I indicate, like for instance, chapter 4, is partially a summary of Macaulay, Winston, and Green. Now, again, Macaulay, Winston, and Green is a very old book, right? There is only one edition. Nobody has revised it, so it's very incomplete, right? So basically, you will see in this chapter that we're going to start today how it differs. So the first part is very similar. I'm trying to keep, the notation there and so on. It started like that, but as we go through, especially to the final theorem, this is really move away from that. So again, the main resource is not the book, is the notes. Okay. So, okay, so having said that, right, so please read chapter 3 if you find it useful. We're going to start right now with chapter 4. So this is part of the main class, and the only reason I'm starting right now is because I want to do it with more time, right? So it's a heavy chapter, so you want to let it sink in right before the class. So you have all the questions, so you have longer than usual, and possibly the only time you have a break between classes, right? So you can ask me questions and so on. So this is chapter 4, which corresponds to chapter 1 in Mascolel, okay? And this is about preference and choice. So the current notes are partially based on Mascolel. So it's gonna have new material at the very end. It's a short chapter, but it's hard. So we're gonna do it very slowly, okay? Yeah, Martin, you have any question?
Yeah, so you already gave a theorem for the utility function without including continuity. What is the difference between the two theorems?
Yeah, so the difference is fundamentally the choice set. The first term that we prove is a finite choice set, right? When you add continuities for a general choice set that allows, for instance, infinite bundles.
Okay. Okay.
Yeah. So what you're missing basically is the choice set. Okay.
Thanks a lot.
Yeah. So we're going to start with preferences and choice. This is Mascolel with some green partially based on that, chapter 1. And what you're going to learn right now, is basically that in order to do real science, we need also to have data, right? So right now we just talk about models, right? Preference is a model, a utility is a model, and now finally we're going to introduce something that you can measure, right? This object, is a choice, rule, or correspondence. Okay, so a choice or rule or correspondence is the object of interest in this chapter. And this is essentially, a description, a mathematical description of choices from choice situations, menus, budget lines, for instance, but they can also be other choice situations. And then out of them, the consumer will pick a subset of the choice set, right? In particular, when you are forcing the decision maker to be decisive, they will choose one alternative out of a menu, right? So say today you want to go for lunch, right? And your options are 3 items, right? So either get some fresh fruit, you get a sandwich, or you get, some fries. This is your choice set, right? If you are forced to pick one item, that will be the choice function, right? So a description of the choice set to the actual choice, which is a singleton out of the menu. If, for instance, you're allowed to be undecisive, so you still want to make up your mind later, so you say things that are choosable, you can also say, I may have fries or the sandwich. And that, in that case, is a full subset. So in particular, choice, rule, or correspondence is going to be a description of choice. I'm going to do it formally in a second. And then we're going to connect it with the 2 items we already know, preference relations and utility functions, okay? So these 3 mathematical objects, right, are going to be connected, and we're going to describe the connections among them. And the main purpose of this class is essentially trying to derive empirical implications of our rational theory of choice, okay? So rationality, as you know, has been described now in a dual way by transitivity and completeness, right? And by maximizing a utility function. We know there is an equivalence, right? We provided a representation theorem. Now we're going to show, okay, let's say I believe this, I want to study this model. What are the empirical implications of this model in choice? Okay, so let's introduce now a choice environment or choice structure. So take X being an abstract, non-empty choice set. So what is an empty, non-abstract choice set? So mathematically, it's just a set that is not empty. It can be this set can be made up of many things. So examples I can have, for instance, lotteries, right? So say tomorrow you can buy a lottery 1, lottery 2, lottery 3, right? And then this is going to be your choice set, right? So it can be basically lotteries. Now, what is a choice correspondence? So a choice correspondence is a mapping from the power set of this set minus the empty set to the power set. So in other words, if I take C, the choice correspondence of menu A being, a subset of X, then the choice correspondence has the restriction that this is a subset of A. Okay, so in other words, a choice is just a subset of a menu. Now notice that I'm not forcing the choice to be a singleton. Okay, so you can have more than one item pick, or you can not make up your mind completely and say, I'm indifferent among this set of alternatives inside this menu, right? So this is a choice correspondence. Okay, so in particular, I'm going to give you a description of the collection of menus or choice situations. So this is going to be denoted as calligraphic beta. And this is just a collection of the power set. So an example. So what is the power set of L1, L2, L3? So the power set is just the description of all possible subsets, right? So how many subsets do I have here? Who knows? Out of 3 items, how many subsets can I form?
It'll be 2 to the power 3, right?
2 to the power 3, right? 8. So including the empty set, right? So no, my restriction here is that no empty set, right? So you have 1 less, right? 7. And then, the singleton menus are also boring, right? Because, out of the singleton menu, essentially, what are you going to pick, right? So we're going to just remove that. And, one particular collection is this one. So I'm just going to imagine that this is L1, L2, and L1, L2, L3. So where does this calligraphic beta or collection of menus comes from? This comes from an experimenter, right? So the experimenter collected money and was able to run just L1, L2, and then L1, L2, L3, right? And this can also be, a natural experiment. So initially there were 2 lotteries in Ontario, right? So Lotto Max and other. And then a third competitor came. So you have L1, L2, L3, right? So that's two choice set situations, right? That's it. So how do you generate choice set variation? Mainly you can think in this class that there is an experimenter, varying the menu, okay? Or alternatively, from real life, you can also get it when there is some sort of variation that generates choice set variation, right? Typical choice set variation is, for instance, when there is a new competitor entry in the market, okay? Do you understand? So basically, this calligraphic beta is a description of the menu variation. So first thing, just recapping, you have a choice set, 3 alternatives, right? And then you have a collection of menus out of these 3 alternatives. The only restriction of the collection of menus is that it's not empty, right? Otherwise, it can be anything. In particular, it cannot be the full choice, the full power set. It can be something smaller. In this particular example, I just have 2 menus. Okay, what is the minimal size of menus you need to test rationality? I'm going to tell you already, you need at least 2. Okay, so if you have just 1, you cannot test rationality, right? Do you understand? Because there is no way you can tell whether you are maximizing. You just see choices from one fixed menu. Okay, you need at least 2. We're going to understand this better in a second, but you need at least 2. So typically, you can imagine that the calligraphic beta, the collection of menus, is fundamentally at least 2 menus, okay? And then let's describe the choice correspondence. So what is the choice correspondence? The choice correspondence maps, as you can see from generically, right, from power set, but in reality, you only observe the choice correspondence in the collection of menus. So you're gonna get a restriction of the true choice correspondence to the calligraphic beta. So I'm gonna get data from these menus. So C applied to L1, L2, which is menu 1. I am creating this data, so it's my invention, comes from my mind, right? Is equal to L1, okay? So this individual decision maker when given menu L1 and L2, lottery 1 and lottery 2, she chooses L1. Okay, this is data. I observed it from an experiment, right? And then when given L1, L2, L3, the same consumer chooses L2, L3. So I'm going to ask you a question right now. From seeing this information, can you tell me whether this particular choice structure, right, in particular choice data, is compatible with rationality? So yes or no? So this now finally you see choices, right? That's the only thing we can see. You cannot see utilities, you cannot see preferences. Do you agree with that statement? It's very difficult to basically see preferences. They live in the mind, right? The thing you see is choices. You see menus and you see people choosing from these menus. So I get an experimenter. This experimenter gets money to run 2 menus. So he provides L1, L2 to this decision maker, and L1, L2, L3 to the same decision maker. From the first trial of the experiment, the decision maker picks L1. And from the second one, this decision maker says L1 and L2, L3. Is this data compatible with utility maximization, yes or no?
It seems not.
It is not?
It
Yeah.
seems so. No.
Not ratio.
Yeah, so give it a try.
Yeah, because in the first choice, the decision maker prefers L1 to L2, but in the second case, she seems to be preferring L2 to L1. I don't know if that's correct.
Yeah, so yes, it's correct. But one thing you say, right? So basically assume right now that this data is generated by a utility maximizing person, right? So under that assumption, L1 being picked out of L1, L2 will imply that L1, is of course has higher utility than L2, right? However, in the second situation, again, keeping the reasoning that this comes from utility maximization will imply that L2 is greater than equal than L1, right? So obviously, because L1 is not picked, there is no indifference possible. So these things must be strict, right? So there is a contradiction, right? Because this is implying that the utility of L1 is strictly greater than L2, and at the same time, the utility of L2 is strictly greater than L1. Okay. So also, Irina also, I think, had the same idea, right? So this is something that is obvious. Now, this is really cool. So you see now that utility maximization, in fact, has testable implications. Okay. So from seeing just choice data, you can tell whether a consumer cannot be maximizing a utility function, right? Without knowing the utility function. Did you realize that? So you don't have to estimate the utility function to know this, right? Do you understand? So right now yep.
Sorry to interrupt. Is it still a contradiction if the consumer prefers L1 to L2, but they don't prefer L1 to L2 and L3 together? Like, as a first reaction, it looks like maybe they're not comparable because now you have 2 things and maybe combined they're better than L1 was alone versus L2. Does that factor in at all?
So that's a really cool question, but remember that mathematically we're describing here alternatives as basically L1 or L2 or L3. When we define a choice correspondence, what we're saying is basically you're undeciding, or basically you think L2 and L3 are fundamentally choosable, right? But you're not thinking that you're going to consume them at the same time. So what you're thinking is another kind of data set where you have preference over menus. So basically you can bundle up L2 and L3 and make something better than L1, right? So mixing them. So, but the data set you're thinking, Sabren, is basically what is called choice over menus. And this is choice over alternatives. So the information that the choice correspondent is giving us is not that they are going to consume L2 and L3 at the same time, but rather than this consumer is declaring that they cannot make up their minds between L2 and L3. So they declare them as choosable, right? Or indifferent among them in the reveal terms. So that's a great question. So yeah, so choice correspondences, again, so they are easy to write down, easy as a mathematical object, but are hard to understand empirically, right? So if you find them odd, you're right, you should ask questions, right? Because they are odd. I mean, this is an object, theories invented in the 60s, right? So, we should really run them through the common sense and whether they in fact appear in real life and in real data and in experiments. Remember, all the guys that invented this never saw a data set in their lives. So, we have to run them through common sense and modern lenses, right? So the question Severin asked is really good. So what is, I was going to say, a word there, but what, is this choice correspondence that I'm bringing to the table, right? So what is this actually describing, okay? And, this is a mathematical object, right? That we basically bought it from Mascolo, Whiston, Green. We have to think what is the empirical counterpart, seriously, right? So the first thing, right, is that, in many experiments, experimenters will force you to choose one alternative, right? So there is not even the possibility of having L2, L3, right? So this is kind of a typical format of experiments. A lot of people use this. I think it's widespread. They force you to pick, right? So they will force you to pick one alternative. And, in many situations, you have, in fact, to choose one alternative out of a menu. So you cannot choose many. So first thing, we're interested in this class only when choices are basically exclusive. So you are going to choose something, and that implies you are leaving the rest as an opportunity cost. So that's the interest of this class, right? So what Severin described takes us outside of the scope of the class. So don't think of that for this class. It's basically, if you choose L1, you are leaving on the table L2, right? And the way, people are thinking about choice correspondences in Mascolo, Whiston, Green kind of people, they were thinking of this as revealing difference. And, the way they actually were thinking about this is, imagine, for instance, I run this experiment many times with the same decision maker. So I give you L1, L2, and I don't give you L1 and 2 just one time, but several times, right? Imagine I got money to give you the same menu 3 times, right? And every time I saw you picking from this, you pick always L1, right? So in that case, the choice for sure is L1, I'm done. The choice correspondence now from L1, L2, L3 is trickier because I gave this decision maker the same menu 3 times. The first time this person picked L2, the second time it picked L3, she picked L3, and the third time she picked L2 again, but never L1, right? So basically what you're taking is you're kind of tabulating choices, in 3 repeated trials, and you're just annotating the instances, right? L2 happened one time, L3 happened one time, L1, it never happened, right? So hence the choice correspondence is L2, L3. So you can also think of it as repeated choice and seeing of the instances that happen. Now, importantly, the guys at the time of, the guys that wrote this in the 60s, 70s, they didn't care about frequency, right? Because you were imagining that experiments were so hard that you're never going to be able to do it very frequently, right? So counting the fact that L2, L3, the one happened 2 times and the other happened 1 time, that information we didn't care because it's just, kind of noise. So we're going to throw it away and we just care the instances, right? So these are choosable items because they were chosen at some point, right? Now, you can imagine that that definition is also problematic, right? Because what if, for instance, I keep asking this guy with the three items forever, right? Imagine 100 times, right? Maybe at some point, that I didn't have the money for, this person will pick L1, right? So how I am sure? Well, you're not, right? So these guys are imagining that somehow this is exhaustive, that is a theoretical object. So I run this enough such that I am sure that it's only L2, L3. Okay. Yeah. So choice correspondences are problematic to be measured. So in particular, in many instances, you only have choice functions where you only are picking singletons. But the reason people keep using them is because they provide you with some apparently encoding of an important behavioral phenomenon. Important, quote unquote, is up for us to decide. People in the 60s thought that indifference was important, right? So the fact that you cannot choose between L2 and L3, but you can also, see the issues with that. So it's very hard to measure whether it's true indifference only from seeing choices, right? So have in mind that choice correspondences mathematically, means that you basically think these 2 items are choosable, right? Or basically they can be indifferent. So this is kind of a revealing difference situation. But it's not the fact that you're going to consume them together, right? You are in the end are going to consume one of them. So essentially, there is a hidden assumption that somehow there is some tie-breaking rule you're going to use and then essentially pick one, right? Okay. So that's implicit in this theory. Okay. So
Professor,
yep.
is this related with, you know, the paper that you sent us about products? That is something called context dependence utilities like this. If you include L3, it's like you change the context. Yeah, and because of that.
Okay, so that's a great observation, Juan Sebastian. So indeed, when you introduce a third object, right, and suddenly you change preferences, right, that can be an instance of context dependence. But let's make a difference, right? This is data, right? So I'm imagining an experiment and giving you this, right? This comes from some, brain I invented, right? So this is data, and you see just menus and choices out of that menu. What you're doing, Juan Sebastian, is trying to rationalize this data that is not rational, right? So in other words, right, so you're providing a new model, given that rationality failed, as Martin and Irina pointed out, you can see that rationality is failing. So of course, the natural next step is to try to find a model that will fit this data, right? Now, but yes, that's a second step. So we are still not there. Right now, what we want to make sure is to be able to create a full test, a full map of what it means to be utility maximizing, right? And how does it look in terms of data, right? So what is the empirical content of utility maximization in choice correspondences, okay? And we're just gonna focus on that on this chapter. And yes, you basically can use this machinery to test real life data. And in real life data, we can start detecting, these violations of rationality, one of them being context dependence, right? And then, of course, if in fact these violations are meaningful, statistically, and they become, something that is established empirically, then you can start creating new models, right? So you're jumping a little bit too ahead, but yeah, it's correct, okay?
Thank you.
Yeah. Okay, so first thing I'm going to do is I'm going to link preferences to choice correspondences, okay? So I'm going to say C, a choice correspondence, is rationalizable when C of A, of any menu, is equal to this set. This set says, are all the alternatives B in the menu A such that B is preferred to A for all A, okay? Now, everyone understands this definition. Is just how I define a set, right? So take all the items in capital menu A, and the property of the items that I'm gonna keep in this set are the ones that are always above, according to my preference ranking, right? To any other item in the menu. Remember that due to reflexivity, right, that is implied by completeness and transitivity, B is indifferent to itself, right? So that part is always active, doesn't matter. And then you're only checking that B is above the rest, right? So this is a set of maximizers. Notice that there is no claim for uniqueness. So the choice correspondence, in fact, can be bigger than a singleton, can have more than one alternative, right? So it's a set. It's not a singleton, okay? Any questions here? So
here by definition, C is already complete without assuming, no?
No, so C is not a preference, it's not a relation, right? So C is just a set.
Okay, sorry, the preference is inside C.
Yes, the preference that
With that-
rationalize C, that's the definition, right? So C is a set, right?
Yeah.
And this set is equivalent to this other set.
Okay, and in that other set, the preferences are already complete without needing to
Correct.
assume complete. But yeah, it is necessary to assume that they are transitive as well.
So
is-
my definition, this is a definition, right? So I say a choice correspondence is rationalizable, right? When this set here is equal to this second set, and this set is generated by a transitive and complete preference. Only then I call this rationalizable. Okay?
Okay.
Yeah. So
In
Yep.
the bracket, B is preferred than is preferred over A, and I think B in the bracket it indicates that B should be a subset of A, and for the other part of this sentence, the latter part it says for any given A belongs to B. I assume it should be B is a subset of A.
so no, so calligraphic B, right?
Yes.
Graphic B is a collection of menus.
Oh, okay.
Yeah. Okay. So the collection of menus defined over the choices, right? So now this is just saying that you take a data, right? That basically, like in the example, has the example here, right? So we have the two menus, right? So this is just requiring that you are able to create this equivalence of the observed choice with something generated by a rational preference function, right? In fact, the maximum set of that particular relation for all the menus in the collection of menus, right? So this is the data set, right? That's my definition. Okay. Everyone is fine? Okay, so that's a definition, right? So I call rationalizable choice correspondence, right? I say C is rationalizable. So this is a definition. This is the property I'm defining whenever something happens, right? And what happens here is that I require that C of A, the data, the choice data, is equivalent to the set of maximizers, right? According to this preference relation in this menu. And this preference relation is required to be complete and transitive, right? And I also introduced this notation that is modeled from Mascolel that says, if I put a star on top of the C, right? This is a shortcut for this menu, this set here, right? So the set of maximizers, right? So in other words, when you see C star, preference comma A, it means, right, that this is the set of maximizers in menu A according to that preference relation given by the symbol, okay? So that's the notation. This is data. This is a model, okay? So data model. Yeah, that's it. So there are two things that are being put in equality of, so basically equality of sets means that this set is weakly contained in the second set and this second set is weakly contained in the first set. That's equality of menus, right? Equality of sets. Done. Now, so we have a data and we define it to be what it means to be rationalizable. And now, you know, we are gonna, this is a part that Mascolel has as kind of a preamble for doing some proof techniques. I'm just gonna state the proposition and leave the proof for you. The proof is super trivial, but we just need to do some things with the preference relation. So we have a binary relation, right? And then, as we remember from the order theory part, we can define basically the asymmetric part, which is the strict preference, and the indifference part. So you take in particular a rational preference relation, and you're going to have the strict preferred to and the indifferent to, okay? And they are defined as we did in the order theory part, as you are strictly preferred to B whenever you are preferred to B, and B is not preferred to A, right? And you are indifferent whenever A is preferred to B and B is preferred to A. And if that happens, then you're going to get some properties of the parts, right? Particularly, this thing is reflexive and transitive. The symmetric part is instead reflexive, transitive, and symmetric, so equivalence class, as we declared it. And then also you can have that transitivity whenever you have a strict part and a weak part, basically will be preserved with a strict part. So these are easy to remember because remember that a rational order behaves like the greater than or equal to symbol in the real line, right? So essentially, you know, that's basically telling you the properties we kind of know. So if you have a number 2 greater than 1, right? And then 1 is greater than equal than 2 over 2, right? So then, you know, essentially, of course, the first number is going to be strictly greater than the second number. So the proofs are, again, practice for logic. So please do it at home. They are kind of long, but it's just breaking down the statements into pieces. So I'm not going to do it in this class. And then we're going to focus instead of trying to motivate a little bit what are the issues with the model, right? And this is basically from Mascolel. I'm trying to think, you know, the main restrictive part of the model, and then trying to understand how this will generate empirical implications. So I'm going to give you, you know, the main punchline here is that the main feature of the rational model, complete and transitive, is not completeness really, right? So completeness is something that puts everything together and is able to deliver a utility function, as we know from the previous part. But the main part that is testable really is transitivity, right? That's the part that is driving things together. And the question, you know, that we have been asking as decision makers is whether transitivity is a good model, right? So Mascolel, you know, is a little bit apologetic here. So he basically takes and says, you know, transitivity may be problematic. And he mentions some things that were known at the time. And, you know, and all of them are kind of context dependence issues. The first thing that he brought to the table is just perceptible differences, right? And then he puts an example about colors. So say you want to paint, for instance, your new bedroom, right? When you are moving, you know, to a new place, you want to paint it. And then, you know, you're choosing among different colors. And you know, you have a gradient of colors. So if you start looking at differences between, you know, blue number 1 and blue number 20, right? And if you compare blue 1 with blue 2, I cannot see the difference, you know. Versus my wife, she can see it, you know. She's also studying design, so she, you know, she can see difference among colors. I cannot see them. So blue 1 and blue 2 is the same for me. My eyes cannot tell me the difference. But if I'm told, look at blue 1 and blue 20, I can see the difference and I can create a preference. I can say this is better than that. So what happens with how indifference is broken here, how transitivity is broken here? What happens is that, you know, if I'm asked in binary comparisons, is it blue 1 better than blue 2? I would say I'm indifferent. Is blue 2, you know, different from blue 3? I say I'm indifferent, right? And I can keep going, right? And essentially, you know, then I can be asked in a discrete way, is blue 1 better than blue 3? They said, actually, I like blue 3. So I was saying 1, 2, and 3 are indifferent, right? And then this should imply that 1 and 3 are indifferent. But I'm then telling you, no, in fact, 3 is the strictly preferred to 1, right? So that's, you know, an instance of what is called just perceptible difference. So when given binary comparisons of things that are close apart, are too close to tell apart, you will be able to say, I'm indifferent, right? So I cannot perceive the difference. But when the difference keep growing and I'm able to do a kind of a discrete comparison, then I'm going to jump and my preferences are going to reverse, okay? And that will be breaking transitivity. So that's a classical example. That's modernly an instance of what is called inattention or misperception, right? So you don't understand the attributes of the alternatives in a sufficient way, so hence you will be able to rank them incorrectly, right? Framing effects, this is a big name, right? So frames, formally, there is a paper by Salan and Rubenstein. They define formally what is a frame. Frame is essentially something of how you present alternatives that they don't change the ultimate payoff of the alternative, right? That's at least the most innocuous way of understanding frames. So an example is like, imagine you go to a restaurant, right? And this restaurant, you know, has a menu. You know, if you analyze each alternative and what you want from this restaurant, the main dishes, essentially it shouldn't matter the list or the way they are ranked in the menu, right? So you should analyze them for their attributes, right? See which one you like the most, right? So what thing you're craving for and whatever. But in reality, right, they are presented in a list, right? So some things appear first, Then, you know, there is a second item and so on. So most menus are list format, right? And think of some alternatives that are very low in the list, right? So do many people check all the menu, read all the menu? I assume a lot of people don't, right? So I'm the guy that goes to this option. So I want this, right? So second or third one, I'm done, right? So very few will go through the whole menu. So there are list effects in the sense that if you were, you know, fully attentive and, you know, you were given the full alternatives, you know, by a very dedicated waiter or waitress, and, you know, they tell you every option, you know, make you understand it, right? Like, you know, in a French restaurant. So they force you to understand what the chef did, the creation, right? Then you will decide, you know, upon your better judgment. But in, you know, due to the frame, which is the list, right, you will end up picking other things, right? So that will change, you know, your preferences in ways that are not consistent with rationality, because the way I present, you know, the menu will change your preferences, right? Things that are presented first will be picked. So then I can generate intransitivities just by changing the list, right? So that's a classical example. And that's even more salient now in our current world because of search results, right? So Google plays all types of tricks with your mind, right? The same as Amazon. So they are always running experiments with you, basically randomizing lists, sponsoring stuff and so on. So you will look intransitive, right? Because you will be picking, you know, things that are by design easier to pick according to the frame. Shelves positions, right? So you go to a store, you know, you go for your preferred cereal box, and then, you know, they display a new one, you know, in a shiny box. Sometimes you pick it, right? So but that's a little bit different. But my point is that, you know, there are positioning effects that shouldn't be consequential for choice. However, you know, they will affect choice and they will make your choice look basically intransitive. And you know, and here comes one classical one. So Condorcet paradox. So who knows who is the Marquis of Condorcet?
He's a French philosopher and writer. I think it was in the 1800s, or I'm not sure of the timing, but
So the French Revolution time, right?
Yeah,
So
yeah.
and he was also a mathematician, right? So he was in
Yes.
fact one of the founders of mathematical social science. You know? And you know, this guy, you know, eventually he ended up, I think, beheaded, or he committed suicide because he was going to be beheaded anyway. So whatever, right? So, but basically, why he was trying to be the social engineer of democracy, right? And you know, he was hoping that, you know, given that under the, you know, humanism, if everyone is rational, then, you know, coming together in a group and voting through democracy will create also kind of rational behavior, right? So sad for him, you know, he found a paradox. So, you know, imagine you have three individuals, right? This is the Mascolel less political example. So, but, you know, a little bit outdated also, but, you know, you have a mom, a dad, and a child, you know, and then they have, you know, this is Mascolel example, not me, so don't cancel me, cancel Mascolel view mass. No, but, you know, whatever. So you have basically O, R, and I, which in Mascolel example, they are opera, rock concert, and ice skating. And supposedly, according to Mascolel preferences, right, in his family, I guess. So the mom preferred the opera to the rock concert and then to the ice skating, right? The dad preferred the ice skating to the opera to the rock concert, and then the kid prefers the rock concert to the ice skating to the opera, right? So the dad is really a fan of, you know, Disney on Ice. So now, you know, you have here the choices out of majority, right? So let's vote. If I may compete O versus R, who wins? So let's go preference by preference, right? This binary voting. So O versus R, mom votes for O. O versus R, dad votes for O, right? So you have a majority, so O wins. Now let's compare R versus I. So R is better than I for mom. R is better than I for the kid. R wins, right? Now let's go for I versus O. So I is better than O for the dad. I is better than O for the kid. I wins, but then you have a strict preference. O, you know, is better than R. R is better than I, and then I is better than O, right? So this is a failure of transitivity, right? So you fail. And then Condorcet was, you know, he already foresaw what was going to happen to him. democracy is messy, right? So voting is not easy. You don't generate transitive things by voting. You generate cycles. And since then, no mathematicians have figured out what is the best voting mechanism, right? So this is an open question. People are still writing papers trying to propose the best voting mechanism that makes things work. So democracy is tricky, but it's also for us, it's cool because it hasn't been solved in Condorcet. Be careful, right? Don't end up like Condorcet. But this is a cool subset of the microtheory, so social choice. Also, like in terms of job prospects, unless you get into Silicon Valley creating an app, it's not a great field. But there is computer science are taking over basically. So they are more data driven. So if you like it, do more the empirical stuff. This was super hot in the 70s, 60s, so everyone was doing. And then you know the famous arrow impossibility result. He showed that a set of axioms basically are incompatible among each other, and that basically killed that literature. That basically, those set of axioms basically include the fact that you kind of behave rationally, right? So you have to be basically transitive, and at the same time, you have to be not dictatorship, right? So those two axioms interact in mathematical ways such that it's impossible, right? And hence, if you want to be transitive, I don't know why you would want to be transitive in the first place, right? But that's the arrow impossibility theorem, in short. And he showed, that if you want to have non-dictatorship plus transitivity, then basically it's impossible. So, then it killed the field. So that's great. If you do a dissertation that kills a field, good for you. But, there are ways to kind of recover it. But, after that, things has been going downhill. Yeah, but one example of this is basically telling you that if you have multiple criterions, right, rationality is failed. However, I already gave you another model, right? So imagine even that you forget about majority voting and you do unanimity, right? So if you do unanimity, then you will recover transitivity, right? You just use completeness. So there are things like such as unanimity that will, of course, recover transitivity. But then what happens with that? You're going to end up being incomplete. So you cannot decide, right? Because you never reach unanimity, right? Like the example we did. So, but short story, if you have multiple people deciding, then you don't look rational. Why should we care? So if you are dealing with data, you go to a survey. The data you get from surveys usually is not data generated by single individual decision makers. For instance, I'm married, right? So when we decide what to buy, we do it together, right? So there is some sort of aggregation of preferences, right? So, and in this case, you're just seeing choices out of entertainment, right? So there is some social scientist checking, I'm gonna do a decision choice model of entertainment choices, right? So you get opera, rock, and ice skating, and then you are facing with these family choices, and it looks crazy, right? It's just because people are taking decisions inside the household. Mainly they are rational themselves, right? So the mom is transitive and complete, the dad is also transitive and complete, the kid is transitive and complete. But when they aggregate their preferences, in this case through majority voting, the output choice will not be compatible with a single utility maximization process. Do you understand? So that's a little bit the message here, is that be careful when data is aggregated from multiple units of decision. In particular, household data from surveys, usually is not rational, but it's not because each individual is rational, it's because you are aggregating preferences, right? So the preference aggregation is hard, Okay, so that's basically it.
So sorry, Professor. So just to get so social choice theory here, which we discussed, means that because you have different groups and these groups are made of many individuals, sometimes they won't follow the axioms of rational choice, and that's why you get certain violations, and that's why it's important to study the effects when you don't have the axioms working properly.
Yeah, I think that's correct. If I get what you're saying, so you have to basically be careful of data generated by groups of people, right? So there is no reason why utility maximization should be at play there, right? Especially if these people are aggregating preferences in very weird ways. So don't do it. So utility maximization is a theory of the individual decision making, right? And to be clear, it's not a tested theory, right? So it's a hopeful theory that sometimes works. That's the claim. but it's very tractable and nice because it reduces dimensionality, but it's not a theory of group behavior. So don't use it for groups. Okay, that's what I'm saying. Okay.
Professor, so microeconomics now merging with psychology?
Yeah, so
Yeah.
psychology, is focused on the individual decision making, and individual decision making. I think decision theory and decision science is a single object that overlaps psychology, econ, computer science, philosophy. So how people choose. That's a question that concerns to all of these groups, right? And in fact, I have interacted with people like that, and now econ is kind of interesting because out of all theories of behavior, the most successful one has been, in psychology and in econ. Philosophy has lagged behind, and computer scientists, they kind of copy us. They have this crazy regret minimization business, which is not great, but essentially, psychology and econ are pushing forward. We are the most successful ones, and but in fact, I think it's a single object, right? How to make decisions. Now, in econ, of course, we focus in more econ budgets. So you're going to focus a lot on budget lines and how to choose from budgets, right? When you have bundles and you have some limited amount of income and prices. That is less studying other setups, but the most abstract is common to psychology. Yeah. So right now, we're just gonna restate this thing we proved the previous class. So a preference relation can be represented by a utility function even only if it is rational. So complete and transitive, x being infinite. Okay, great. So we remember that. So we know that utility function is general, but it has some issues. Let's try to get the empirical content. Okay, so the first time I'm gonna give you empirical content. So give me a data set. So a collection of menus and a choice correspondence, right? So this is choices from menus. The weak axiom of revealed preference warp is a name that Samuelson invented, right? Weak axiom of revealed preference, right? Which is the warp. So Samuelson was great at naming. He basically was imagining an axiom so weak in the sense that so easy to be satisfied by humans that it must be the center of human consistency, right? Of course, he was too hopeful, right? But we're going to discuss that. So he called it that. And what is that? If there is some menu V in this collection of menus, such that X and Y, two alternatives are there. So there is at least two alternatives there. And we observe that X is in the choice correspondence of B, right? So in particular, it can be pick. X is pick out of menu B. Then take any other alternative menu B prime that is different from the first one, where also X and Y are there. Okay, so B prime also has X and Y and potentially can have other items, right? Like the example we have, lottery 1, lottery 2 is the first menu, lottery 1, lottery 2, lottery 3 is the second one, B prime. So B prime is a different menu from the first one, however, containing X and Y. And I happen to observe that Y is in the second choice from menu B prime. Then we must also have that X is in C of B prime. So that's a lot to digest. Yeah.
Just one question. So why did we have to choose X? Why couldn't we have chosen something that's even better than Y and X? Or are we just assuming it's just those two?
So why we have to pick X? That's the question exactly, right? So X is being picked from the first situation. And in the first situation, Y was affordable, right? Okay. So according to the rationality, right? This is connected to rationality. It must be what possible instances we have if X is pick. So it can be that X is strictly preferred to Y, or that X is indifferent to Y, right? But it cannot be that Y is strictly preferred to X, right? Because if that happens, then X wouldn't be here. So there is only two possibilities from this observation. Do you understand? So either X is indifferent to Y, or X is preferred to Y. There is no other possibility. Do you understand? Okay. Now you go to the second menu and you observe that this person picks Y. So at least remember, you can also be indifferent. So now if you have picked Y in the second situation, then I have the first possibility that X was strictly preferred to Y is no longer possible. So the only possibility that remains is that Y and X are indifferent. So if X and Y are indifferent, then it must be that X is also chosen from the second part, right?
Yes, okay, that makes sense.
Okay, but it's a mouthful. I agree with you. The first time I saw this is, okay, so this is weird. So let's try to write it in an alternate way. Okay, so we're gonna write the weak axiom revealed preference with alternate notation and introducing a new concept called revealed preference. And when we introduce the new concept, revealed preference, I hope things make more sense. So we're gonna restate the weak axiom using this new concept. So new concept, revealed preferences. Revealed preferences are the invention of Samuelson. And then basically he says, look, I cannot see your preference. I cannot see your brain. I cannot know exactly what you like, you know? So, and also Samuelson is assuming he doesn't believe you if you tell me you like something to something. So he is ignoring all your claims that you like A to B, right? So, you know, he's ignoring that. So he's saying, I'm just gonna look at your choices. I'm gonna ignore anything you say, right? I cannot look at your brain directly, so I'm just gonna see what you choose. And then I declare that A is directly revealed preferred to B with this notation, A in relation with B, but with this super letter capital D, right? So when you see the symbol, right, is direct revelation, right? And whenever A is chosen, right, from menu B, and capital menu V contains item B. So Samuelson is saying, look, it is reasonable to believe that if you choose A, when B was available to you, I can say, you know, that you're revealing to me directly that A is preferred to B. Do you agree with this definition, right? So it seems reasonable, right? So from observing your choices and your choices alone, if you choose A whenever B is available to you, you say A is revealed preferred to B. Okay? Any questions there? So remember the key here is that B has to be in the menu, right? Okay, for instance, if you have L1 and L2 and you choose L1, then A is preferred to reveal prefer to L2, but you cannot infer anything about any other item that is outside the menu, right? It's only about menus that are present, only about items that are present, okay? So first thing, now I'm gonna refine this definition. So I'm gonna say, we say A is directly and strictly revealed prefer, denoted as A in strict relation D with B. Whenever A and B are in the menu, you pick A out of capital menu B and you don't pick B, right? So if on top I observe from the choice data that you are not choosing B and you're choosing A, then I declare A is strictly and directly revealed preferred to B, right? Makes sense as well. And here comes the part that is more interesting and deeper, right? So we say A is indirectly, right? So is indirectly revealed preferred to B, and we basically name it with the star. So preference star. This is because of masculine. It's kind of bad notation, but whatever. But if you have a star there, right? So this is indirect revelation. If there is some sequence of items, A1, A2, ... AN, such that there is a chain. A is directly revealed preferred to A1, A1 is directly revealed preferred to A2, ... AN is directly revealed preferred, and this is missing, to B. Okay? So do you understand? So Samuelson says, look, from observing your choices, imagine, I never see you choosing really A and B together. So there is no menu that has them at the same time, okay? But I observe instances of smaller experiments where I see that you pick A, when A1 was present. So I say A is directly revealed preferred to A1, and then I see A1 versus A2, and I see you pick A1. And then I see A2 versus A3, and that AN, I see that is preferred over B. Then I can put them together, and then I can jump the shark, right? I do this inference, and I say, you are telling me indirectly, right, that A is better than B. Under the indirect, we just call it reveal preference relation, I'm saying A is reveal preferred to B, okay? So all of these three definitions are just definitions, right? They are not a proof. They are not a theorem. They are just a definition Samuelson invented, right? And he claims these things, are useful because they are going to be used to impose this condition that is going to reveal the empirical content of rationality. And then we're going to write, using this new definition, the weak axiom of reveal preference. So the weak axiom that I just described here, I'm going to write it in terms of the reveal preference relation. So we say, warp, if X is directly reveal preferred to Y, then Y cannot be strictly reveal preferred to X. In notation, X in relation D with Y implies that not Y strictly directly reveal preferred to X. Okay? Do you understand? So this is the weak axiom of real preference. So the weak axiom is of course a definition that is putting a restriction on the reveal preference relation that I infer from data. And now I can prove the following result that is great, amazing, because this is connecting for the first time a model of utility maximization to an empirical content, something I can check on data, right? So something that I can actually check in data. I can run an experiment and check the weak axiom, and I can do a scientific inference from it. So let the symbol represent a rational preference relation, and then say I have some menus, and then I have, remember this C star notation. This decision maker is maximizing their preferences in these menus, right? So generating this choice correspondence C star. Okay. So this is the notation I introduced some minutes ago. Then this generated data satisfies the weak axiom. Okay. So remember that Martin said, this choice correspondence can be complete. So the choice correspondence cannot have properties of preference relations, right? It's just a set. So this choice correspondence is defining many sets. So it becomes basically a mapping that lives on sets, right? And is mapping to subsets of the sets, right? So this mapping I define from the power set to the power set. So this is a form of a function. So it's a set value function. And this is a property of a function. So warp is a property of choice correspondences, right? If the choice correspondence is rationalizable, then it satisfies warp, okay? So let's even do it like this. So imagine I have choice correspondence, right? Satisfies work, okay? So I'm even breaking it even more. So let's do that, right? So if C of A, right, is rationalizable, it means that it's equivalent to this C star of the preference relation in the menu A, which is exactly equal to B in A, such that all the alternatives B here are better than A for all A in the menu, right? And this preference, as we know, is complete and transitive. Okay. Okay, so now with this in hand, take two menus, right? Just the definition, B and B prime, and take X and Y in the intersection of these B and B prime, because two menus have to have the same X and Y, right? That's my requirement of the first definition. Now, if X is in the C star choice correspondence, right? And Y is also in the choice correspondence of the second one, this must mean, by the definition of the sets, that X is preferred to Y and Y is preferred to X, right? Then by the definition of the preference, this means that X is indifferent to Y. This implies that X also belongs to the C star of the B prime, right? By definition. So because X is preferred to B for all B in B prime, given that Y is preferred to B for all B in B prime, and X and Y are indifferent, then by transitivity follows that X also has to be here, right? So I just use all the properties again, and then I'm going to conclude that warp holds, because warp, as defined here, said that if I observe this, the premise for some menu that has X and Y, and then if I observe also that Y is picked from the second menu, then conclusion, we must also have that X is there, right? You can also prove it using the notation of the direct reveal preference relation, and I guess it's going to be shorter and easier, so you can do it as an exercise at home. But what I want you to stop now is to contemplate this result and to basically go back to our example. And what I'm telling you here is that if you have some data generated by a utility maximization model or rationality by a complete and transitive relation, then the data generated by that model will satisfy at least the weak axiom of reveal preference, right? Okay. So now let's go with these tools to the example that we did at the beginning of the class. Okay, so let me copy it. And we're just gonna take it and try to see if it satisfies warp. Let's put it here after warp. Yep. Warp fails. So who wants to give it a try? So let's write the direct reveal preference relations, right? So first, from the first, from C, L1, L2, right? We conclude that L1 is strictly reveal preferred, sorry, to L2. Do you agree? And
Yes.
right, from C, L1, L2, L3, conclude that, sorry, I didn't put the output of this, L2, L3, right? We conclude that L2 is strictly reveal preferred to L1, right? To L1. So this is a violation of warp, right? Hence what? So look at this proposition. It says, if you're rationalizable, then warp. So then what happens if not warp? So if warp fails?
Either they're irrational, right? So we would say that they're irrational here.
Yeah, so it's just the contrapositive, right? So if not warp, not rational, right? So basically, if you fail warp, then C is not rationalizable, right? Okay, so that's just the conclusion, right? Because if you're rationalizable, then warp, then it means that if not warp, you're not rationalizable, right? Just the contrapositive. Understood? Okay.
Yes.
Yeah, so that's great, right? So actually I created a test that just needs 2 menus, and I can tell you right away if you're rational or not. Okay. And as Juan Sebastian say, the claim in behavioral econ, marketing, psychology was that you can generate this very easily from context effects, right? Like the frogs of the podcast, right? So in that example, when you move to 2 to 3, because there was this decoy. So an alternative that was basically distracting you and making it more hard to compare among alternatives, right? Then these people change their choices, right? And so it seems to be that humans, frogs, and in general, any individual with a finite brain, you have infinite bandwidth, will typically fail the weak axiom, right? And Samuelson, what was his motivation when doing this? So his motivation was saying, look, people criticize us as economists in the 60s because we're doing models with something you cannot observe. So preferences and utilities are not observable. So if you do, if you're theorizing about things you cannot measure or observe, what are you doing, right? So you're not scientists, right? So the solution for Samuelson was saying the following. He said, look, I don't have data, but I have intuition, I have my brain, right? So I'm gonna invent now something that in principle can be measured, which is a choice correspondence. This is something an experimenter can go and try to get. Do you agree? Right, so that's the claim. So once we have our data, the choice correspondence, now I'm going to impose a condition on observables. And this condition is going to be called the weak axiom of revealed preference, right? This is a restriction on choice correspondences. This is the weak axiom, okay? Once I do that, right, Samuelson claimed, this is so weak, so natural, so logical, my brain will always satisfy it, right? That all the consumption theory should be founded on this property alone, right? That was what he wanted to do, his vision, right? He said, and why he was so confident about it? Because the weak axiom of revealed preference, if you go to this statement here, what it's requiring is that you don't flip your preferences, right? So this is a minimal consistency of choice. So if you first choose X over Y, then you cannot flip your preference. You cannot backtrack on your choices and say, now, I actually like the other. But of course, this example I created, inspire everyone by the frogs, they actually do that, right? So they first, prefer strictly L1 to L2, and then they suddenly flip their preferences, right? You see? So why this is going on, right? So why Samuelson was wrong, for the frogs case and for many cases with humans, is because he wasn't based on data, right? So it's not like he's doing like a physicist, right? So trying to see a lot of experiments and start looking at a pattern that arises from data, right? Samuelson, as many other theories at the time, he just used intuition. He said, I'm so pure and smart that, I will never flip my preferences, right? I'm a consistent guy. I'm a man of my word. No, I'm just kidding. But of course, he was not using real data. He was using intuition. That's the capital sin there. The original sin, as I'm a Catholic, by formation, not by practice. And we have this notion of the original sin, right? So what is the original sin of this theory? Is that it wasn't based on data, right? So the weak axiom of revealed preference, it was a restriction on fictitious data that when we actually were able to measure it, because that was the big jump that Samuelson did, is he created an object that you can actually measure and then actually test the weak axiom, right? And then, it came out that the weak axiom is failed. Moreover, Samuelson also thought that the weak axiom was different from rationality, right? And it's a little bit different, but it's not much different. And the first result that we established is basically that if you have preferences that are generated by rational behavior, then you satisfy the warp, okay? So we also know that warp, in fact, ended up being a test for rationality. Now, Martin will ask me this question, so I'm gonna go ahead of him. So what happens about the reverse question, right? So imagine you satisfy warp. Does it imply that there is a preference that rationalizes the data? So this is one way, right? So the arrow goes from left to right, saying you're rationalizable, hence you satisfy warp. Now, what about the opposite? Say you satisfy warp. Yeah,
That's
so
always.
But this is different from the definition that we saw previously because the previous definition went in the two directions.
Yeah, but we also, my main point is that we also want to know the opposite arrow, right? Which is the next part of our study. So what happens now, if, for instance, if you are satisfying warp, can we say something about preferences? Okay, that's what we're gonna do next. Okay. So remember, so this is just a reminder.
We cannot.
So it depends on the data structure. So the first result in Mascolel says that if you have a data structure such that every up to 3 element is included, so you have included the tuples and the triples, right? And also, you know, an important assumption here that I didn't include in previous years, so I have to make it even more explicit here, right? With the implicit assumption that the choice correspondence is non-empty, right? Then, you know, basically the fact that you satisfy warp implies that there is a preference relation rationalizing C. So Martin say no because in general, this is false. We're gonna have an example in a moment, but it is true for a special kinds of data sets when you have 2 and 3 elements. So you have all possible binary experiments and all triples. So basically from this agent, you show this person in an experiment, all AV, VC, CD, right? And all AV, CD, all the possible triples and tuples. If you have such a very rich experiment, and on top, the consumer always chooses something, so the choice correspondence is non-empty, right? Then this is true, okay? Now, again, this is tricky because this is a very rich data and you're assuming the consumer always can choose something from the menus. So they somehow are able to maximize, okay? So under all of these conditions, you know, there is this known result in Mascolel where basically he shows that satisfying the weak axiom will guarantee the existence of a preference relation. Now, this year, actually, I'm going to do something different. So I'm going to prove this in a bit, but let's first understand the whole picture and then let's go back to the proofs. So I want you just to understand that right now we're trying to go in the other direction. So take a choice correspondence. It satisfies warp. Then can I learn something about preferences? The answer is yes. In fact, you are going to be rational and I can recover some preference relation if and only if this experiment contains all tuples, all binary menus, and all triples, right? If that happens, then you're golden, right? You can recover a preference relation. And in fact, you know, basically you're rational, as if you're rational. You can never know for sure if someone is rational because you cannot see their mind and you cannot see their choice process, but you can assume they behave as if they are rational, right? So that's the statement here. And we're going to prove it, but before proving it, I also want to give you the full picture. So then the next natural question is, what happens if you don't have such a rich menu structure? So imagine you're a real life experiment and you cannot offer the decision maker or the subject all possible tuples or binary menus and all possible triples, right? And imagine even that the consumer, you know, sometimes doesn't want to choose. So you don't force the consumer to choose, right? So sometimes says, I'm confused. I don't know what to pick from this menu. So indecision is allowed. So imagine you have that. And now, so we're going to define a strengthening of the weak axiom that is going to be called the generalized axiom of revealed preference. And this is called the GARP. Okay. So the GARP requires more than the weak axiom, of course. And this is going to say the following. So we say a data set satisfies the GARP if for any x and y such that x is indirectly possibly, it can also be direct. So this star revealed preference relation includes the direct revelation and the indirect, right? So remember it's both there. So it's either or. So x is revealed preferred to y. Then there exists a chain of items, xi, indexed from 1 to n, such that x is directly preferred to x1, ... xn, and then this is directly referred to y. it is not the case, right, that y is directly and strictly will prefer to x. So in other words, right, so if you have indirect revelation of x to y, there cannot be direct revelation of y to x. So this is extending the weak axiom, because the weak axiom is only requiring that you cannot flip in direct revelation, right? So if the weak axiom only requires that you cannot have direct revelation reversals. The GARP, in fact, is ruling out not only the direct revelation reversal, so it includes the warp, but on top requires that you cannot reverse on indirect revelation. Okay, so if you indirectly reveal to me that x is better than y, then also you cannot now change your mind and say, now I like y strictly to x in terms of reveal preference. Okay, so now I'm going to show you some examples, and this is part of the problem set, I think, in the first problem set, where you can actually show that the weak axiom and the GARP, the generalized axiom, are different. So there are data sets that pass the warp but fail the GARP. Okay, so I'm going to give you this as part of the problem set. But what is the theorem with this strengthening is the following. So the following two statements are equivalent, logically equivalent. So the one is even only if statement. So one, even only if two. The choice structure dataset calligraphic BC, a dataset of choice, satisfies the GARP. This is equivalent to the choice structure dataset BC, can be rationalized by a rational preference relation. Okay. So in particular, you know, one thing I want you to have here in mind is that the thing that changed between theorem 7 and this proposition that is based on Mascolel is the type of data we have. So Mascolel is assuming that you have all elements, all menus up to 3 elements, right? And he calls this the rich data set. Okay. He's also assuming that the choice correspondents are non-empty. However, as I say, in many cases, you don't have the rich data set. So in general cases, it turns out that the fact that you pass the weak axiom is not sufficient for being rationalizable. Okay. The necessary and sufficient condition is not the warp, but the strengthening, the GARP. Okay. So you need more. You need the generalized axiom reveal preference. So we're going to do the proof. And because I want to go slow today, I'm just going to first focus on the example, and then we're going to go to the proof of the generalized axiom. So I'm going to give you an example which shows, you know, that that is a different data set where you can actually test rationality. So let's say I have 4 items, A, B, D, and E. And then I have the following menus, right? A, B, B, D, and AD. So this is not a rich data. Why is not rich? Because it doesn't include the tripletons, right? So there is no tripletons in this collection. Now, say from the first AV menu, you choose A. Then from the second, you choose B. And then for the third one, AD, you choose A. Now you basically check the reveal preference relation. You see that A is directly preferred to B, B2 directly preferred to D. And note, and basically you also can observe that it's not the case that D is directly preferred to A. So that means that GARP holds. Now, my theorem is assuring you that once you have this assurance of GARP, then it must be that your choice correspondence can be rationalized. So can I generate basically a preference function that is rational, complete, and transitive, such that it generates the particular data pattern I observe here? So obviously the answer is yes, and we can verify it by a construction such that E is preferred to A is preferred to B, and B is preferred to D. So as you can imagine, in neither of these things, E is present, right? So E can be positioned in any place. So, but you can nevertheless generate a complete and transitive relation that generates the data. Okay. Now, as part of the final part of the class, you know, and the proofs, we're going to end up with a proof in the last 10 minutes. I want you to try to generate now
Can we put E there even though we've basically seen nothing of it up until the end? We sort of assume it goes in front of A, or perhaps behind D. We're free to throw it in wherever.
So that's a good question, Severin. So this is, we have to separate two things. The thing we're doing is testing, and basically we are verifying, yeah, that some data sets satisfy some conditions. So GARP satisfy. So when you do that, the claim is that there is existential quantifier, a preference relation that generates the choice pattern, right? So when I say there is, it doesn't mean that there exists a unique one. So you're adding an additional thing, a property, which is called uniqueness, right? That is related to something called identification. So it's very rare in this very general setup that you can identify preferences uniquely, mainly because you have partial data sets. So if you were to observe all possible binary menus, in fact, you can pin down uniquely the preference relation, right? So namely, here you don't have any comparison between any of the items and E, right? So if you have more experiments, right, where you can see E being put together in a menu with other alternatives, then you can infer essentially the preference relation. But so what I'm just telling you is break down what we want to do. Right now we're doing testing and finding one particular preference relation that does the job. Is not the unique one. And you are asking uniqueness. This is a second step, which we haven't done, which is identification of preferences. So yes, and the question is, are we allowed to do this? Well, if I'm asked to do welfare analysis, right, you are in all your right to ask me why E is considered the best thing if it was never really chosen in any real life situation, right? Basically, I can do it because there is no data, but it doesn't mean I should do it. So it's can versus should, right? So the fact that, you can create this preference, there is also another preference where E is at the very bottom, right? And then it also works, right? So the only thing you know is that these preferences are set identified. So you recover a set of preferences that do the job, right? So that's the full answer, but just try to break it, right? So this is testing, and what you're asking is identification, right? Okay, so now I want you to generate a choice correspondence pattern out of the same A, B, D, and E that fails GARP. But, so that's the first question. The second is, you can do it one in the same. You can also do it that generate a choice correspondence that satisfies work but fails GARP. Okay, if you're able to do it one, we're done. So again, you can use the ABCD. You basically need 3 alternatives to make it fail. And in fact, for the first one, it should be easy. For the second one, is trickier, right? So that one, I think, will be left for the problem set. So I want basically you to generate a choice correspondence that satisfies work but fails GARP. So who wants to give it a try for the first one? Just something that fails GARP. So tell me the choice from a menu, and then we can do basically a simple pattern that breaks GARP. That, of course, it should be GARP and not, not a simple one like word violation, right? So you can start from simple menus, right? So AVA. Then you have AC. That would be the simpler one. But let's do something a little bit more trickier. And then you have the one that can break everything, right? What is the example that will break it, that will generate basically a violation of GARP?
Sí, you need to choose sí.
Okay, so you have now C, and this thing fails GARP, right? Because you have the following. So violation of what? Of the items, right? So this is just the chain. So there is an indirect revelation, and this is a violation of that. Question here, is this a violation of warp?
No,
No, why am I?
because if you look at all of the choices that he's made, there's no choice that violates the rationality or the transitivity, right? Property.
No. So the reason, right? Just go back to the definition of warp, right? And definition of warp requires that there is no direct reversal of preferences, right? So, for instance, A is better than B, right? So for a reversal of preference should be that A and B are together again, right? In some menu, and then now you pick strictly B over A, right? That would be a violation of warp. But A and B never appear together again, right?
Yeah. Yes. Yeah. That's correct.
Okay, yeah. So just come up with another one yourselves and prove it completely, right? So I'm not proving it here. So for the problem set, you do a violation of the word. Now you can see now the difference, right? Why here, even so they satisfy warp, right? You cannot create a rational model to generate this data because this is not a rich data. So in this data, I only have double tones, right? And I don't have the triple tones. So the Mas-Colell theorem fails, right? Because the data is not rich. And of course, what was failing is GARP, right? So you can satisfy the weak axiom, but fail the generalized axiom, okay? So that's the punchline. So now in the last 10 minutes, I'm just gonna do the proof for the GARP part. And then please read the proof for the previous proposition, which is the one in Mas-Colell. So this one is not in Mas-Colell, right? But it's in my notes, as I mentioned, okay? So sufficiency, what does it mean, sufficiency? It means one implies two. So imagine, and this is the hard one in the 10 minutes I have. So the choice structure dataset satisfies GARP. I'm gonna show that the choice dataset structure can be rationalized by a preference relation, okay? This is the hard one, okay? So first define, I'm gonna define a candidate preference relation, right? This is just a definition of the asymmetric part of the revealed preference relation, right? So this in the definitions, we were also naming them like this, right? But you have to be careful because here the preference relation contains the indirect and direct preference revelation. So I'm just gonna define it as this is A is preferred to B, but B is not preferred to A in the indirect revelation. Okay, that's my definition of this object, asymmetric part, and you can see it here. Now, GARP implies that this preference relation, the observable direct preference relation, is inside this other preference star, right? So preference star in the strict part is a little bit bigger, is a bigger set, but of course the direct preference revelation is there. Okay, so it's a subset of that. You can see that clearly, right? That's very easy to observe. Now, notice as well that this preference relation star is in the transitive closure of this preference relation D. So what is a transitive closure? So if you go to the order theory part, the part that I asked you to read, you take some possibly incomplete preference relation, right? And then you basically verify that this relation is acyclic, right? And then you can basically make it complete in any way you want, preserving transitivity, right? And preserving the strict revelation should be the same in the completeness part, in the completed extension, right? So I'm gonna give you some examples for this, but the operation is an abstract operation, right? So what you have to do basically is start with an incomplete relation that is not transitive, but is acyclic. And then you basically take the extension such that it makes it complete. So you're ranking every unranked item. And you do it respecting the strict preference part and the closure. So basically the completed version of this previously incomplete preference relation happens to be transitive, right? That's a transitive closure. And when you do that, right, this is always doable when you have an acyclic preference relation. And acyclicity is basically GARP. As you can see, the definition of GARP is essentially the definition of acyclicity that I gave you in the order theory part. So what I'm going to do is basically I'm going to take this preference relation that is in the transitive closure of this D. Then we can use proposition 1 in chapter 1 in the order theory. So we can go a little bit backtrack the part that I asked you to read. This is the extension is a Split-Strand extension theorem. So, and then to claim that there exists a complete and transitive preference relation such that X is preferred to Y implies that X is preferred to Y in the preference relation that I'm defining as the transitive closure of this star relation, and that the strict part implies that is also strictly preferring the new part. So this means basically that X belongs to C of A implies that X is directly preferred to Y for Y in A, and this implies that X is better than Y for all Y in A. So why? Because now you have a complete and transitive preference relation that respects the observed data, which is the star data. So the fact that you're chosen here immediately means that you must be above the rest, because if not, right, you wouldn't be chosen. So chosen, this is the maximum element. So the property is that you have to be above the rest. And when you are not here, this implies that there exists a Y, right, such that Y is directly preferred to X. This implies that Y is strictly preferred to X and not X strictly preferred to Y. So together, this implies that C is equivalent to X of the set of maximizers, right? Now, so the proof here is coming from the fact that we can take an acyclic preference relation and we can complete it. Now, in order to unpack this proof, I want you to do the following. So first of all, notice the definition of the generalized axiom reveal preference, right? So this is an acyclicity condition. I'm taking basically a chain from X to Y, and then I'm assuming that Y cannot be strictly related to X, right? So this is a special case of acyclicity, right? So in particular, there is no loop here, okay? Do you agree with that? So now I want you to go to order theory, right? And you can go to proposition 1. This is the part I want you to read. And in proposition 1, we're going to have this Split-Strand in theorem 1. We have this Split-Strand extension theorem, where we show that a partial order can be extended to become complete, right? And in particular, we're going to have some corollaries that I want you to read as well. And this will basically provide kind of the mathematical foundation of the existence of this transitive closure. So you can basically go and come back to this order part and read the Split-Strand extension theorem for filling in the blanks here of what you need to prove it. But in particular, right, the proof of what we saw today relies on the simple fact that when we have an acyclic preference relation, we can always extend it and make it complete, such that the extension is going to be a transitive and complete preference relation. So as you can see from the example, in this particular GARP example, this preference relation, that is the direct preference relation, can always be completed, right, in arbitrary ways. So in particular, this example here is an example of a completion. So this is a transitive closure, right? So E is better than A, better than B, better than D. This thing is complete and transitive, right? And this one, of course, includes this information derived from here. So A is better than B, B is better than D, and D is better than A. Severin asked, where is E, right? So E is not ranked, so this thing is not complete, right? So the fact that it's acyclic means that I can extend it to a transitive and complete thing that respects the strict preference relation, okay? Now, in contrast, let's go to this example where GARP fails. So I say A is better than B, B better than C, but then I have C better than A. Is there any transitive closure that respects the strict part that makes this thing transitive and complete? Not really, right? Because the only way, to complete this and make it transitive is to make everything indifferent to each other, right? But that will not respect the extension, the part that is strict, okay? So in short, this proof is a little bit invoking basically a technical assumption, which is the extension theorem. So it's not the most nice proof ever. And basically we are relying on this Spilsran extension theorem. So I'm not gonna really, be doing this as the main test or, the main proof that we're gonna do. We're just going to do is just clean the house. And then I'm gonna provide in the next chapter in more structured environments with budget sets, I'm gonna provide to you an extension theorem that is constructive, right? And that's gonna be done in the chapter 5, what is called the Affets theorem, where I am going to build a preference relation that is complete and transitive through the construction of a utility function from a data set that satisfies the generalized axiom of revealed preference. And why I cannot do it here, because at this stage, this choice set is so abstract that it's very difficult to construct a utility without invoking these extension theorems, okay? So this is an example of a non-constructive proof using a version of the axiom of choice or the Zorn's lemma. So this is a proof in math that basically invokes the existence of an extension, right? So we say there exists an extension, because if this extension doesn't exist, then the axiom of choice fails, right? So basically the axiom of choice is something that mathematicians like to assume that you can actually take you can select from a set of alternatives one item without specifying that item. And that's what we're doing here. We're saying there exists an extension of the revealed preference relation that happens to be complete and transitive and respects the strict part, okay? And we are assured by this extension theorem, that is another instance of the axiom of choice, that such an extension exists, right? Now, again, it's not the best proof in my opinion, but this is the proof we need at this level of generality, okay? When we move to the other chapter, which takes this a little bit down to earth, allowing for budget constraints, we will be able to prove the Affets theorem, which is gonna give me essentially, as you can see here, the generalized axiom of revealed preference in this more structured world. And then we're able to prove the equivalence of GARP and the existence of a utility function, right? In a constructive way. So I'm gonna build a utility function constructively, okay? And so right now, what I'm just telling you is don't get freaked out by this kind of proof. It's just cleaning the house. I'm just making sure we can use this. But all in all, this has an empirical implication for you. And is that now I can test utility maximization in any kind of data set. So give me a data set, give me menus, give me the choices from the menus. I can apply my test, the GARP, and I can conclude that if you fail GARP, there is no way you're maximizing a utility function. And moreover, if you satisfy GARP, now you are as if you're maximizing a utility function, right? And in fact, I can recover maybe set identified, so not point identified, some information about preferences, okay? In non-unique way. So I'm done today, so I'm 4 minutes past. Sorry about that. But the good thing is, tomorrow, I don't want to go fast in this class, as I say. So I'm just gonna send you the problem sets. These are due from Friday, 1 more week. Feng is gonna grade it. It's not mandatory. It's not gonna count in any way. It's just for your feedback. So when I say graded, it's provide feedback. And so, I'm gonna upload it in the Slack. You're gonna see it. So I'm gonna use the same Slack for the main class. So, I'm just gonna keep some announcements through OWL, so where they are there, the main announcements. But mainly, Slack is gonna be the way of communicating when we start classes. Tomorrow there is no class. I'm gonna submit a video, so you have the extra material for some additional topics of the refresher. But I basically want you to use your time to basically work, if you can, and especially if you need it, on the problem set, right? So, and of course, reach out to me, send me a message through Slack. I can help you through the problem set. So For me, it's more, if you need help, I'd rather use it helping people that need more help through the problem set, right? And so I'm gonna do more personalized in that sense, okay? So that's it. So tomorrow, no class, but there's gonna be a problem set, and I'm gonna be happy to, meet with you by video or whatever. We can do an appointment during this week, right? And then, if you want to work on the problem set. So I'll just expect the problem set. I'm gonna upload it until night. So by tomorrow morning, you will have it, right? And then you can work on it if you want, okay? So we're gonna start basically the class a little bit reviewing this chapter again. So the proofs with more detail and, this extension theorem, more details and so on. And then we can go from basically this last part of this chapter to chapter 5, which is gonna take us a lot of time. If you notice, chapter 5 is really long. It's one of the longest chapters, right? So we're gonna spend a lot of time on it because this is the main core of chapter 3 of Muscular, okay? And that's it. So thanks, guys. I'm gonna stop recording and then I'm gonna be here if you have any